and welcome to Fitting with MATLAB, Statistics, Optimization, and Curve Fitting. My name is Richard Willey, and I'm the Product Manager for the Statistics products here at the MathWorks. Before I begin, I'd like to take care of a few logistical issues. If you have any technical difficulties during the presentation, please use the chat tab to correspond with the webinar host. If you have questions about the content, please post them to the Q&A tab, and we'll do our best to answer them all at the end of the presentation. I'm going to start the webinar with a brief overview of regression analysis. More specifically, I'm going to discuss a type of regression known as ordinary least squares. Ordinary least squares is the default case for regression analysis. When you learn regression in school, you start by learning ordinary least squares. When you use virtually any software package to perform a regression analysis, you're using ordinary least squares. The main reason that I want to discuss this technique is to show you that it's based on a series of assumptions. If these assumptions hold true, ordinary least squares will give you a good result. Conversely, if these assumptions are violated, you might want to use an alternative technique to generate your fit. Next, I want to show you a series of common real-world curve-fitting problems. It turns out that each of these types of problems violates one of the fundamental assumptions that underlies ordinary least squares. Accordingly, you can often generate more accurate results if you use a different algorithm to generate your fit. We're going to see how MATLAB can be used to solve curve-fitting problems when your dataset contains outliers, or when both the x and the y variables contain measurement errors, or where you're measuring counts or estimating odds. We're also going to look at some examples where the assumptions underlying ordinary least squares aren't being violated. However, we still need to broaden the set of techniques that we're using. For example, generating an accurate curve fit when you have a large number of predictors creates an interesting set of challenges. Also, in many cases, you might need to apply a set of constraints to your curve fitting problem. I'll conclude the presentation by showing you where you can get additional information, and then we'll wrap up with a Q&A session. Okay, let's get started. At the most basic level, you can think of regression as predictive modeling. We're trying to predict some dependent variable y as a function of a set of independent variables. More formally, we're often trying to derive the best linear unbiased estimator to predict y as a function of x. As I mentioned earlier, least squares regression makes a number of assumptions about the data that's being modeled. If you understand these assumptions, it will help you understand when it's appropriate to use this technique, and more importantly, when you might want to consider a different algorithm. The first assumption is so basic that many people don't even think about it. We're developing a model that describes the relationship between predicted and observed. Ordinary least squares assumes that all of the variance in the model is associated with the y variable. When we measure the distance between predicted and observed, we do so parallel to the y-axis. We're going to look at some alternative techniques, like orthogonal regression, where the distance between predicted and observed is measured perpendicular to the regression line. Our second assumption has to do with the distance metric we're applying. When we use ordinary least squares, we're minimizing the sum of the squared errors. In theory, there's no reason why we couldn't minimize the sum of the absolute value of the errors instead. In fact, there are occasions when this technique, which is formally called L1 regression, will generate better results. The last assumption has to do with the nature of the error term. Ordinary least squares assumes that errors have an expected value of 0 and that they exhibit constant variance. There are a lot of cases where this doesn't hold true. One classic example is when you are measuring counts or estimating odds. In cases like this, you might prefer to use techniques like Poisson regression or logistic regression. Let's start looking at some practical examples. As I mentioned a moment ago, ordinary least squares regression creates a model that minimizes the sum of the squared errors between predicted and actual. There are a lot of cases where this technique is inappropriate. The most important is when your data contains outliers. Squaring the error term works very well when your errors are normally distributed. However, if you have observations that are atypical, that are far removed from the rest of your data points, then squaring the error term will significantly skew your model. This visual example might help illustrate what's going on. This plot shows a set of data points, along with a regression model that I derived using ordinary least squares. The dataset contains an obvious outlier, which is skewing the regression model. The red curve shows a second regression model that I generated using a robust regression technique called least absolute residuals. I generated a curve fit that minimizes the sum of the absolute value of the residuals rather than the sum of the squared residuals. As you can see, the red regression line does a much worse job fitting the outlier. The distance between predicted and actual is much larger with the red line than the blue. However, the red regression is much more accurate, fitting the remaining data points. Now that we've had a chance to discuss this, let's jump into MATLAB and look at the various options that we have available for robust regression. To start with, I want to show you just how easy it is to use robust regression using a sample data set. I'm going to generate some X data and some Y data that's arranged on a regular grid. Next, I'm going to generate a set of Z data such that X, Y, and Z all fall on a plane. Finally, I'm going to add a noise vector to Z and plot the resulting data so you can see what's going on. It's pretty easy to see that X and Y fall on a regular grid. You can also see the noisy relationship between X, Y, and Z. There are a number of different options for performing regression in MATLAB. I normally use the fit command from Curve Fitting Toolbox because I think that the syntax is easiest and I like working with the fit objects that it outputs. I'll start by using the fit command to generate an ordinary least squares regression. I'm going to model noisy Z as a function of clean X and clean Y. I'm going to pass in the argument poly11, which will fit a plane to the data. The fit command outputs a fit object and information about goodness of fit. Next, I'll use a plot method to plot the fit on top of my scatter plot. Generating a fit using robust regression is just as easy. All I need to do is pass an additional argument to the fit command. In this case, I'm using the argument robust, which instructs fit to use robust fitting. I'm also specifying LAR, which tells fit to minimize the sum of the absolute value of the errors rather than the sum of the squared errors. All these same options are available inside of SFTool. We start by loading clean X, clean Y, and a noisy Z. I'm going to switch the tool over to do regression, and by default it will generate a fit using ordinary least squares. I can check the robust fit option and use either least absolute residuals or an alternative technique which is called bi-squared weighting. Statistics Toolbox contains a cute little demo that you can use to understand just how robust regression works. If you type robust demo, all one word, at the command line, you'll bring up the following interactive tool. You can use your mouse to drag different data points around the screen and simulate the presence of outliers inside your dataset. As you can see, moving data points has much more impact on the red curve, the ordinary least squares regression, than the green curve, which is the output from your robust regression. Least absolute residuals and bi-squared weighting are the two most popular techniques for handling outliers. If you need more fine-grained control, your best option is to use a function called robust fit inside a statistics toolbox. As you can see, the syntax for robust fit is quite similar to the fit command. Robust fit works by applying a weighting vector to the various data points. And by default, robust fit uses the same bi-squared weighting that we looked at a moment ago inside of surface fitting tool. Where robust fit really shines is all the different options that it provides. Robust fit allows you to choose between 9 different weighting vectors, or even write your own weighting vector. The logic behind this is you might want to adapt your weighting vector based on the specific characteristics of the outliers that you believe are going to be present inside of your dataset. I'm going to jump back into my slide deck to introduce the next topic. Ordinary least squares assumes that all of the variance in your model is associated with the dependent variable. If you believe that there is variance in both the x and the y directions, it's more appropriate to use a technique like orthogonal regression, also known as total least squares, also known as errors in variables, also known as Deming regression. This technique measures the distance between predicted and observed perpendicular to the regression line. Here's a simple example that might help motivate when to apply this type of technique. Let's assume that I'm measuring a production process x as a function of time. My test bench has a very accurate clock, so I'm confident that there's no measurement error with my independent variable. In this case, it's perfectly appropriate for me to use ordinary least squares to measure x as a function of time. Now assume that I'm measuring a second production process y also as a function of time. Once again, very accurate clock, perfectly appropriate for me to use ordinary least squares. Now let's make things a little bit more complicated. Suppose I want to measure y equals f of x. Both the x and the y observations contain measurement error. In this case, it's inappropriate to use ordinary least squares, and we can significantly improve our accuracy if we use total least squares. I'm going to jump back into MATLAB and show you a neat little demo that shows how to use Statistics Toolbox to solve this problem. I'm going to start by generating a clean data set. I'm going to add noise vectors to both the dependent and the independent variables. Afterwards, I'm going to go and try to predict the original clean data using both ordinary least squares and total least squares. And as we'll see, total least squares is a much more accurate predictor in this case. One last little note, I'll be posting all of the sample code onto MATLAB Central in the next day or so you'll have plenty of chances to play around with this all. Just like before, I'm going to start by generating an x, a y, and a z variable, where x, y, and z all fall into a plane. And once again, I'm going to add a noise vector. In our previous example, I added a noise vector to the z variable. This time I'm adding separate noise vectors to x, y, and z. Visually, you can see that x, y, and z no longer fall on a regular grid. And theoretically, we're violating one of the underlying assumptions for ordinary least squares. I'm going to start by generating an ordinary least square regression that predicts noisy z as a function of noisy x and noisy y. I'm also going to generate a metric that I can use to measure the accuracy of my prediction. I'm going to generate the sum of the squared errors between my predicted z value and the clean z value that I originally specified. Next, I'm going to repeat this exact same process, only this time I'm going to use orthogonal regression. Bit of background information about the orthogonal regression. Statistics Toolbox doesn't offer a total least squares function out of the box. However, you can use a technique called principal component analysis to perform an orthogonal regression by translating the output of the PCA back to the original coordinate system. For those of you who are unfamiliar with PCA, PCA is nothing more than the application of centering and rotation to a data set. And as simple as this might sound, it's one of the most useful data analysis techniques available. To start with, PCA will center the data on the origin. Next, PCA rotates the data such that the dimension with the greatest amount of variance is parallel to the x-axis. The dimension with the second greatest amount of variance becomes the y-axis, and y is perpendicular to x. And the dimension with the third greatest amount of variance is the z-axis, which is perpendicular to both x and y. So why do we care? Well, it turns out that the first two dimensions define the plane for our regression model. The third dimension defines a set of residuals that's perpendicular to this plane, and voila, orthogonal least squares. So this next bit of code uses printcom to perform the principal component analysis. Next, it translates the output back to our original coordinate system. And finally, it plots the plane predicted by the orthogonal regression. For now, let's just focus on the fact that we have two different planes. We have a red plane, which was the output from the ordinary least squares, and a blue plane, which is the output from the orthogonal regression. It might sound basic, but the two planes are not identical to each other, which means that they're generating a different fit. Next, I'm going to calculate my error term for the orthogonal regression and compare it to the ordinary least squares regression. As you can see, the sum of the squared errors is much larger for ordinary least squares, which means that orthogonal regression is generating a much more accurate model. Let's jump back to PowerPoint and start discussing how to model counts and estimate odds. These types of models present special challenges because the errors don't exhibit constant variance. As a result, you can often get better results using a technique other than ordinary least squares. Let's start with a simple graphical example of a Poisson regression problem. The plot that you are looking at is a set of data points that shows count as a function of time. Hypothetically, this might describe the radioactive decay of an atom or the number of requests for page views on a website. From our perspective, what's important is that the count is always non-negative and discrete. It always takes an integer value. More formally, we're assuming that the count can be modeled by a Poisson distribution. Just by eyeballing the curve, you can tell that the errors don't exhibit constant variance. In the lower left, the area where the observations are all clumped together, the errors will have a relatively small variance. The observations in the upper right are spread apart. Here the errors will have a relatively large variance. Moreover, recall that the count is always non-negative, which also impacts the distribution of the error term. The distribution of the errors is bounded in one direction, since the observations can't ever go negative. This boundary condition crops up a lot when the average is close to zero. If the average is significantly larger than zero, then the boundary condition isn't as important. It won't take effect nearly as often. So our goal is to generate a curve that describes the count as a function of time. At any point in time, the curve describes the average of a Poisson process. We're going to solve this problem using a technique known as Poisson regression. And Poisson regression is a special case of a technique known as generalized linear models. Logistic regression, which is used to model observations that are drawn from a binomial distribution and is typically used to estimate odds ratios, is another special case of generalized linear models. Okay, back to MATLAB. I'm going to start by generating a sample data set. I'm going to create 100 x values evenly distributed between 0 and 15. I'm also going to specify that x and y are related to one another by an exponential curve. And I'm going to plot x versus y so you can see the original true relationship between the two variables. My observations will be a set of 100 random draws from a Poisson distribution. At each x value, I'm going to make a single draw from a Poisson distribution with lambda equal to y. I'm also going to superimpose a scatter plot so we can see the relationship between the average curve and our observations. Next, I'm going to use standard nonlinear regression to model y equals f of x. I'm going to use the fit command to model noisy y as a function of x. I'm going to instruct fit to model the relationship between x and y as an exponential curve. This red curve shows the estimate produced by the nonlinear regression. Visually, it looks like the red curve is doing a pretty good job estimating our true value. Next, we'll solve the same problem using a generalized linear model. Here I'm going to use the glmfit command to model noisy y as a function of x. I also need to specify that we're using glmfit to model a series of observations that are drawn from a Poisson distribution. Please note, unlike the nonlinear regression, we didn't need to specify that the relationship between x and y should be modeled as an exponential. I'll get back to that in a couple minutes. The black line shows the model estimated from glmfit. This curve looks almost identical to the output from the nonlinear regression, and the sum of the squared errors is almost identical. So right now you're probably asking, what's going on? Why should we bother with glmfit if nonlinear regression is going to generate the exact same answer? So to address this, I'm going to run a quick Monte Carlo simulation. I'm going to generate 1,000 data sets. I'm going to use these to run 1,000 nonlinear regressions, and run 1,000 Poisson regressions, and I'm going to go and compare the output. This chart shows the original true relationship between x and y, as well as the mean of the nonlinear regressions and the mean of the Poisson regressions. And once again, the curves look identical. I'd be really hard-pressed to claim that there's a statistically significant difference between either of the predictions. However, rather than looking at the mean of the two curves, let's compare the standard deviations. At each of my x values, I'm going to go and calculate the standard deviation of the 1,000 nonlinear regressions and the standard deviation of the Poisson regressions. And I'm going to create a simple plot that shows the ratio between the two values. As you can see, the standard deviation of the nonlinear regressions is about 1.5 times as large as that of the Poisson regressions for most of the x values. On average, the two techniques are equivalent. However, the larger standard deviation suggests that there is significantly more variance in the estimates generated by the nonlinear regression. There are regions where the two techniques are equivalent. However, on average, the output from GLM fit is a lot more stable. More formally, generalized linear models are preferred because they have a larger scope. A generalized linear model will provide accurate predictions across a broader range of conditions than ordinary least squares. At this point in time, there's a natural question that people tend to ask. That exponential curve, where did it come from? How did you know to pass an exponential curve into nonlinear regression? Conversely, how did GLM fit know that when you specify a Poisson distribution, this implies an exponential relationship between x and y? The answer has to do with what's known as a link function. Any time that you're working with a generalized linear model, GLM fit assumes a relationship between the distribution that models your observations and the curve that you are trying to estimate. The inverse of the curve that you are fitting is called the link function. Statisticians have developed a set of standard link functions that they typically use when they're working with generalized linear models. For example, when they're working with Poisson regression, they assume a logistic link function, which means that you're fitting an exponential curve. If you're working with a logistic regression problem, you assume a logit link function, which means that you're fitting a sigmoid curve. The documentation for GLM fit provides a complete listing of all the different distributions that GLM fit supports, along with the default link function for each of those distributions. Now you also have the option to override the default settings by specifying your own custom link function if you prefer. So far, our discussion is focused on curve fitting challenges that crop up because some of the fundamental assumptions that underlie ordinary least squares regression are being violated. There's another class of problems that occur when the OLS assumptions are valid, however, you need to extend the technique. One of the most interesting set of problems arises when you have a large number of independent variables. This embarrassment of riches presents two different problems. First, if you build too many predictors into your model, you can run into trouble with overfitting. The data sets that we work with include both trend and noise. Ideally, we want to make sure that our models are as accurate as possible at describing the trend without modeling the noise component as well. A model that is overfitting is describing both the trend and the noise. And models that overfit will be extremely accurate in describing the specific data set that you use for training. However, they often can't be generalized to other data sets. Second, in many cases, external design considerations limit the number of independent variables that you can use. Here's a prototypical example. Suppose that we need to build a control system for an embedded design. There's a fixed amount of memory available to implement that design, and as such, there's a hard constraint on the number of predictors that you can build into the model. Hypothetically, we might be limited to no more than 5 predictors. These types of challenges can be addressed using a combination of feature selection algorithms like sequential feature selection and relief F, feature transformation techniques such as partial least squares regression and principal component regression, and utility functions like cross-val and CV partition. Let's start by looking at a simple example using sequential feature selection. Since we are just looking at Poisson regression, let's look at an example that applies feature selection to logistic regression so we can see another type of generalized linear model. Once again, I'm going to start by creating a sample data set. In this case, X is a matrix that contains 10 different predictors. I'm also specifying a weight vector B. This vector describes the influence that the different predictors will have on the final model. Some predictors, like numbers 1, 4, and 10, have a very significant impact. They have a high weight. Others, like number 2 and 3, have a weight of 0 and don't contribute anything to the model at all. I'm going to specify that the average relationship between x and y is described by a sigmoid curve. And finally, I'll generate noisy y as a function of x. Sequential feature selection works by testing whether adding or subtracting variables from the model generates a statistically significant improvement in accuracy. In this case, sequential feature selection will start by adding each of our 10 predictors, one at a time, and determining which variable has the most significant impact on the accuracy of the model. Next, sequential FS adds each of the remaining 9 variables to the model, once again determining which of these variables contributes the next most to increasing the accuracy. This process will stop when none of the remaining variables has a statistically significant impact on the accuracy of the model. Sequential FS outputs a vector named inModel that identifies which features have a statistically significant impact. As you can see, sequential FS was able to correctly identify that only variables 1, 4, 5, and 10 have any real impact on the model. Variable 8 had a positive weight, but the weight was so small that it didn't have a statistically significant impact. Finally, I'm going to rerun my model using the 4 features that were recommended by sequential feature selection. The deviance of the resulting model is identical to my original model with 10 features, showing that the reduced feature set generates the same amount of accuracy. One last note in passing. This example ran quickly enough that I didn't bother to use parallel computing. If you have larger problems that involve very large numbers of predictors, or alternatively, if you're using modeling techniques that require lots of CPU cycles to execute, you'll get a really nice performance improvement if you turn parallel computing on. Next, I'd like to show you a second feature selection technique called relief F. One of the weaknesses of sequential FS is that it considers each feature, each predictor in isolation. Relief F is able to detect conditional dependencies between features. I'm going to start by loading a sample dataset called Ionosphere that ships with MATLAB. X is a matrix which contains 351 observations with 34 independent variables. Y is our response variable. Next, I'm going to use relief F to rank the various features. Now, a couple quick points I want to discuss while the algorithm runs. Sequential feature selection is a function that we wrap around another function. In the previous example, we applied sequential feature selection to GLM fit. Relief F is a standalone feature selection algorithm which uses k-nearest neighbors search under the hood. The number 10 at the end of the relief F command denotes the number of nearest neighbors that relief F is going to use for its comparison. The output from relief F is a column of ranks and a column of weight. Here, I can look at the output and see that feature number 24 is the most important feature, followed by features number 3 and feature number 8. Unlike sequential feature selection, the relief F algorithm doesn't explicitly recommend which of the features should be removed from the model. In addition to functions for feature selection, Statistics Toolbox also offers capabilities for feature transformation. In fact, we already worked with one earlier today when we used principal component analysis. As the name suggests, feature transformation works by transforming the dataset over to a new coordinate system. The 2 most popular feature transformation techniques are partial least squares regression and principal component regression. Unfortunately, a 1-hour webinar really doesn't give enough time to do justice to either partial least squares regression or principal component regression. What I can do is point you at a really stellar demo that we have available on the MathWorks website that compares the two techniques. The demo includes a sample dataset as well as code that implements each of these two techniques. This demo provides a first-rate introduction to feature transformation, and it also includes some excellent applied examples using cross-validation. This leads us to cross-validation. A few minutes back, I discussed problems that arise from overfitting. If you build models that are too complex and contain too many predictors, you risk fitting both the trend and the noise in your dataset. Cross-validation is a way to avoid overfitting. At the most basic level, cross-validation works by dividing your dataset into a test set and a training set. You fit your model using the training set. You evaluate the accuracy of the model using the test set. Your trend should hold constant across the two datasets, while the noise component is independent from one dataset to another. Therefore, this technique will help ensure that your model is accurately describing the trend rather than the noise. Statistics Toolbox provides a pair of functions for cross-validation. CV partition generates an object that stores the folds from your original dataset, while cross-val is used to perform the model evaluation. The last set of challenges that I want to talk about today has to do with constraint. This is another example where the assumptions that underlie ordinary least squares regression are valid. However, we're applying a set of additional restrictions onto the process. Some common examples where constraints get applied to regression problems include constraining the regression line to pass through a specific point, constraining the regression coefficients to take a specific value or fall within a specific range, forcing the regression line to have a positive slope, or for that matter, the third derivative to be greater than 0, or applying budget or weight constraints. Some of the simpler versions of this problem can be handled by Curve Fitting Toolbox. It's easy enough to use fit options to constrain the coefficients for your regression or force a positive slope. More complicated problems are best handled using Optimization Toolbox. Optimization Toolbox offers fine-grained control over your objective function, and you can use this to specify quite elaborate sets of constraints. For our final demo, I'd like to show you a real-world example illustrating what's known as a common slope problem. The example was taken from a paper titled Modeling of Tumor Growth and Anti-Cancer Effects of Combination Therapy by Koch et al. The paper studied the impact of different drugs on the growth rate of tumor. The equation at the top of the slide describes tumor growth as a function of time. Three of the key parameters that the model estimates are independent of the drugs that are being administered. Lambda 0 governs the tumor growth rate during its initial exponential growth phase. Lambda 1 governs the tumor growth rate during its linear growth phase. And K1 describes the transition rate between compartments of non-proliferating cells. And in English, this describes how quickly cells die. The last parameter, K2, is specific to the drug being administered and describes the potency of that drug. We're going to use nonlinear regression to compare the tumor growth profile when two different drugs are being administered. Here's where things get interesting. Three of the variables that we're working with are independent of the drug that's being administered. The coefficients for these variables should be identical, regardless of whether we're administering drug A or drug B. How can we constrain the regression such that both regression models output the same set of coefficients? The answer is a function called LSQ curve fit that is included with Optimization Toolbox. LSQ curve fit stands for least squares curve fit. It can be used for the same type of regression analysis we've been looking at all through this webinar. What distinguishes LSQ curve fit is the fine-grained control that you get over the optimization problem. You get to write your own objective function, and you can customize your function to handle complicated problems like this common slope analysis. So let's jump into MATLAB and see how to solve this problem. A moment ago, I talked about an objective function. The objective function is where we're going to build our constraint. I'll start by specifying my 3 drug-independent variables, followed by drug-dependent variables for drug A and drug B. The data that we're using for our fitting problem is being generated by some simulations with SymBiology under the hood. The next 2 lines of code set up a pair of simulations for our drugs. Notice that variables L0, L1, and K1 appear in both simulations. This is imposing our common slope constraint. Now let's move over to our analysis function and put this to work. We start by importing our data. Next, we specify some starting conditions for LSQ curve fit. We pass our data, our objective function, and our starting conditions to LSQ curve fit and start the simulation. Finally, we display our output, which consists of a set of 3 common drug-independent variables, along with drug-specific parameters for K2. I really love this example. I think it does a great job illustrating how powerful the optimization functions are. Not only did we impose a common slope constraint, we were also able to link the curve fitting to a pair of dynamic simulations. Now obviously this example is specific to biopharm, however the same basic use case crops up frequently across a variety of disciplines. So it's time to wrap up and then move on to some Q&A. To start with, I'd like to provide a quick summary of the techniques that we looked at today, along with some of the MATLAB functions that can be used to solve these problems, as well as the toolboxes where you can find the functions. As you can see, most of the algorithms that we're looking at are located inside a statistics toolbox. However, curve fitting toolbox and optimization toolbox certainly have their place for solving these types of problems. Next, the MathWorks website has some great demos that provide much more in-depth treatments for some of the topics that we've discussed today. I want to draw your attention to the following demos. Partial least squares regression and principal component regression. As I already mentioned, this demo provides a great practical example of feature transformation. I can't recommend it highly enough. Selecting features for classifying high-dimensional data is a great applied example for feature selection. It's based on a classification example rather than regression, but the techniques and the algorithms are all the same. Fitting data with generalized linear models. As the name suggests, this is a nice demo of GLM fit, which uses a logistic regression example. Finally, fitting an orthogonal regression using principal component analysis goes into a bit more detail regarding orthogonal regression. Equally significant, all of the product documentation for Statistics Toolbox is available on the product page. If you're trying to get a feel for the capabilities of the product, this is another great place to start. Last but not least, we have a great recorded webinar titled Tips and Tricks, Getting Started with Optimization Using MATLAB. This webinar is a great guide to our optimization capabilities. So, give me a minute to look over some of the questions that have come in, and then we'll move on to Q&A.